Welcome back, everybody. So we have a few more seconds so that you can reach your seats. So I'm very happy we took the hour to do this. The trick for teaching, for learning is called spaced repetition. That's something that was popularized by Duolingo, which was created partly by ETH, by an ETH former students. The idea is to repeat the same thing at a specific interval, like every week, every 2 weeks, and then the brain at some point memorizes. So we just repeated things today, but because we did that, that should help you store in the long-term memory what we've learned. Don't hesitate to ask more questions. Send us an email to Bojidar, to me, to your TA. Ask questions in the exercise sessions. I told the TAs to note down the questions if they don't know the answer. I'm very interested in understanding all the areas that might need clarifying. And to make you feel good, you're pushing the boundaries of knowledge further than last year. This is why all of these questions. And that's because last year they already asked questions that pushed the knowledge as well. And so you're just pushing it further. So a lot of the questions are already quite advanced. So let me continue then to something that hopefully should be easier. Who finds it easier? Data modeling, schemas than HBase? Yeah, it's a bit easier, right? So very practical. So let me continue this. So last time I taught you JSON, and now I'm going to show you another one. This one is actually popular. JSON was made for teaching purposes and also to try to bring more types. So JSON's, what's going on? Okay. My computer is just making its own decisions, it seems. That's very interesting. Yeah, okay. So JSON schema. If you're scared, then you're right to be scared. It is a bit more verbose than JSON. And also, I told you I was shortening a little bit because you should read the book and the textbook and learn it. And so I made it a bit shorter in the lecture to not bore you with repetitive descriptions. So let's look at it. What do we see first? Well, first, the schema is also a JSON document, just like a JSON schema, right? So it's very common in schema languages that we use the same syntax to express the schema than the one with which we express the instance, right? So remember, instance is what we call the document we want to validate. Schema is what we call the description of the constraints that we want to enforce. So now you see, I'm saying that I want to enforce that I have an object. And these are the properties that I recognize. And if the property is present, then it has to be this type. Now you see a bit more complexity because I have this extra object with type and so on. That is how JSON schema works, right? And one of you spotted that in the textbook, I forgot to put the type object in some examples, but this is fixed now. You just need to re-download the textbook to be sure. You really do have this object type descriptor in there, right? But basically what it tells us is that this is a string, this is a string, this is an integer, this is a Boolean, and this is null. And as you can see, it's valid. Who agrees that it's valid? Okay, very good. So that's the first exposure. Now, you shouldn't be surprised that I'm able to specify what is required and what is not required. I could do it with the exclamation mark in JSON, if you remember. Well, here it's just different. Of course, every language does it differently. We just have a required schema property in here for that object that says that last and first are required. And the others are not required. So last and first, they are here, so that's fine. Age happens to be here, although it was optional, and physicists always null, they are optional because they are not in the required list. And so this document is valid against that schema. Who agrees? Right, okay. Very good. So this is about optional required. Now, what about extra fields? You remember that in JSON, we could allow or not extra fields. You remember that in the compact version of JSON, the one I showed you, we do not allow extra fields. Right? Anything that is not in the schema is disallowed. Right? If you want to allow it, you would need to use the verbose syntax, but this one is not something that they expect. You just need to know it exists and you can do it, but don't need to know how. So the way we do the same thing in JSON schema is with the additional properties field. That's what we called open or closed, open objects and closed objects in JSON. So if it's false, then it means it's closed. you don't allow anything that's not in the list. If it's true, which is the default in JSON schema, then you allow anything. So concretely, that means that here you are restricting to just last and first and nothing else is allowed. And if it were true, you would allow anything else. Remember that the rule with open object types, when it's open, additional property is true. The rule is that if you have an extra field or property or key, whatever you call it, then anything goes. It can be whatever you want it to be. It could be an object, an array, a Boolean. You just don't care. If you allow extra properties, they can have whatever value they want. But if the property is in the schema, then it has to be of the specified type, right? Who is with me? Right? Okay. Then let me continue with the structured types, because of course in JSON we can have nested structures. So you can see how now it's becoming verbose with the JSON schema, because there's a lot of hierarchy in there. So let's look at it. There's an object. What are its properties? Well, name and theories, right? So name is here and theories is there. What is name? It's a type object. You see the recursion in here. And that object in name has the properties, well, last and first, string, string. These are strings. And then the second property, theories, is also, it's not an object, it's an array. So we have type array. You see, it's an array. And it has sorry, it's made of objects, right? So we need to say in the JSON schema that it is an array, and the items of that array, so whatever is in the array, it's always called items here. Every item of the array, every member of the array is another terminology, must be an object. So it's an array of objects, and every one of the objects in that array must have if name is present of type string, and if here is present of type integer. And that is the case right here. So who agrees that the instance above is valid against the schema below? More raised hands? Take the time to look at it. You agree, right? Who doesn't agree? Nobody disagrees. Okay. So you see the logic, right? We have the schema really specifies the layout that we expect in the structure. Who sees that it's more verbose than the JSON equivalence? Right? In JSON, we would have something that closely resembles the instance, right? Name, last string, first string, theories, array of object, name, string, year, integer. That would be the JSON schema. But here there is in JSON schema a bit more nestedness. That's how it is, right? Okay. So what do we have next? Oh, another feature that actually we also have in JSON in the verbose syntax, but in JSON is very important in JSON schema. Because in JSON schema, you have very few available types. You basically have object, array, integer, number, string, Boolean, null, and that's it. You don't have much else. And for this reason, it's more important in JSON schema to have restrictions like this to further constrain these few types. So in that case, you can say not only is it an integer, but it has to be within this range, minimum and maximum. This idea of further constraining types is very common in schema languages, right? You can do it in JSON, in XML schema, in JSON schema. You can really specify intervals. For strings, you can specify the maximum length of a string, the minimum length of a string. You can also have an interval in which the string must be, lexicographically, of course. So you can have a lot of constraints like that. And in fact, even though it's not done here, but technically when you do that, you are in fact defining a subtype. Right, so this is a subtype of integer that is constrained to this interval. Who is with me? Right? So again, remember here that most schema languages allow you to specify that sort of things, to constrain an interval of integers, to constrain the length of a string, to basically be more fine-grained. It's all about constraints, really. It's all about imposing constraints on the document so that you can say that it is valid. Okay? What else do we have? Yes. What if you want to allow for any type? So in JSON, you just have item, that is the topmost type that validates anything. In JSON schema, you just use Booleans because the JSON schema is basically a Boolean matching system. So true means it matches anything and false means it matches nothing, right? So Name true means you can have whatever you want in there, even anything else than that object. And theories means you can have whatever you want. That could actually be absolutely anything in there. You just consider it as valid. And other, false, means it's forbidden. You cannot have this. You could have, because it allows additional property true by default, so you could have others, but not this very specific property, which is forbidden, right? So anything but this one. Who is with me? Right? Very good. And that's what I wanted to show you, right? So this is a JSON schema, right? That's the flavor of it. Okay, so I encourage you to read the textbook. It's a bit more explained in more details with even more examples. And you have, of course, more things. I'm not covering everything, but you have OR logical statements that are basically union types. So this is another concept in schemas. If you want to say that a value must either be a string or an object, or you can also do these kind of things, right? All right. So now we've seen JSON, we've seen JSON schema. JSON schema is very popular. It's used in plenty of systems like MongoDB and so on, right? Any questions so far on JSON schema? Not in the room, on Zoom? Did we get Zoom questions today? Are you hearing us on Zoom? Just to making sure. Is anybody hearing us on Zoom? Is anybody there on Zoom? Yes, awesome, thank you. So there's actually a lot of people on Zoom connected. Okay, don't hesitate to ask questions in the chats too, of course. Okay, so basically what I would like you to see now is JSON or XML, it doesn't matter. These are all trees. And it also, to validate, it also doesn't matter. You also have schemas. So you have schemas for XML, just like you have schemas for JSON. And the idea is exactly the same. A schema just expresses constraints about the structure and the types that you can have in the data.
Question just popped up in
yeah. Oh, yeah. Awesome. So it worked.
Yes. So in JSON, we can have a key that's not in the schema, but in JSON schema, we can have additional properties as true.
Yes, absolutely. So they differ in the default behavior. It's that in JSON, the default behavior is to not allow for additional properties for pedagogical reasons that will become very clear in a moment, right after XML schema. So in JSON, by default, you disallow extra properties. But if you're an advanced user and you know the verbose syntax, you can allow it. You have a way to deactivate that limitation and to allow for additional properties. JSON schema does the opposite. In JSON schema, if you don't say anything, it's allowing anything as extra properties, and you can also change it with additional properties set to false. True is the default. You can either set additional properties to true or just do not even write additional properties. That's the same, because true is the default. Does it answer your question? Yep, awesome. Okay. A word of warning, XML schema is very scary, and I'm barely going to touch the surface. It's very, very complex because there are so many things you can do, which is why I want you to take the high-level approach. It's all about structural constraints in the data and about the types that we accept. So I took a few examples that should be similar to JSON so that you get the idea, right? But since I already showed you with JSON and XML schema, that should be straightforward. So let's dive into this thing. No namespaces, because I don't want to make it even worse, right? You can also have namespaces. You can specifically have a schema for every namespace. As you can imagine, there's a schema for mathML. There is a schema for music, defining music in XML. There's a schema for HTML, and so on. So you can have a schema for every namespace. But in this example, I don't have any schema to just keep it simple. So you can see no schema, no prefix, no colon, plain old vanilla XML documents. Okay, but of course the schema does have a namespace. I mean, everything in the schema is in the XML schema namespace, which is right here. And you can see it's standardized by W3C, which is the World Wide Web Consortium. And it's always that namespace. Typically, people use XS or XSD. You have different tastes regarding this. Some people are very courageous and make it the default namespace. I think it's a bit risky because that might be hard to read if you have other namespaces. But anyway, that's a common one, XS. So we define a schema. You have an element foo that has the type string. Who agrees that this is valid? Yes, you agree, right? This is text, period, is a string, right? So we all agree on that, okay? But there is one thing I didn't say. Did you notice that the XML schema is a well-formed XML document? Who noticed that? Right? It's that same logic, right? JSON schema is a JSON document, a JSON schema is a JSON document, an XML schema is an XML document. There's alternatives to XML schema like schematron, RelaxNG, and so on. They are also XML syntax, right? It's not always the case. There's a few exceptions. Protocol buffers, for example, they would store the data in a binary fashion, but the actual schema would be a text file that has a specific syntax to protocol buffers. That's a Google technology. But anyway, back to this. The schema is also an XML document. And it looks like this. That's a very small schema that just says we have an element called foo, whose value inside must be a string. So that's the first one. Other example, here I put integer right here. Who agrees that this here is valid? Okay. So if I want to be very highly formal, what I need to say to justify that it's valid is that this sequence of characters that is technically before validation is just text in the info set. Who remembers it's just text? There's the text information, character information item. It's 1, 4, 2, 8, 5, 7 before we validate. So technically what happens is that this sequence, 1, 4, 2, 8, 5, 7, the sequence of characters, is recognized as being in the lexical space of the integer data type. In other words, you can read it as an integer, as 142,857 in base 10. That's what it means, right? So who agrees it's valid? More right sense? Okay, very good. Okay, so it is valid. And by the way, because that's less to learn, all of the types that you can put in there, the atomic types, are exactly the same list as those you have in JSON. It's the same. And that's also the same one as in JSONic. That's all the same. This is a W3C standard, and everything is following the standard, JSON, JSONic, and so on. So that's just that one list. And I gave it to you last week. There was this huge slide with all the listed types. Who wants to see it again? You don't want to see it again. Okay, so you can just watch the video and see it again. I would have had to rewind a little bit. Okay, so there's a menu. It's the same menu for JSON, for XML schema, or for JSONic, right? As opposed to JSON schema that has just a very limited list of just a few. Okay, now what about structure? Because that's easy, that's flat, right? But what about structure? Well, it's the same idea that in XML, we define the structure. Don't be too scared. I know it's very scary, but what do we want to say here? It's simple. I want last and first, and I want a string inside. Very similar to what we did in JSON. So basically, I say, okay, my element here, that's called person, is a complex type, complex because it has children, a hierarchy, and so on, that has a sequence of elements. The first one is last, and it's of type string. We agree it is, right? Last has type string. And the second one, in this order, the order is important in the children of elements in XML, not the same as in the JSON object. Element first of type string. So this is last and then first, both of type string, within person, as children of person. I want plenty of raised hands. Who agrees that document is valid against the schema below? Right, awesome, very, very good. So that is an example of a complex type with complex content, but we just want to say we allow specific children in some elements. I can also have multiple occurrences of the same. You can repeat them in XML. We actually did that. If you remember the orders, order, and so on, you can multiply, have multiple times the same child. That's very typical in a data set. When you have nested tables. So here I have an element that are very originally that I called 2 to 4, and I say it can appear between 2 and 4 times. And then I have the element 0 or more that can occur, it's optional basically, and it occurs 0 or 1, sorry, not 0 or more, 0 or 1. So either it's not there or it's there once. Who agrees that this here document satisfies the schema there? Plenty of raised hands. Very good. You see it's the right order. 3 occurrences of 2 to 4, that's between 2 and 4, so that's fine. And 1 occurrence of 0 or 1, that's fine. And the first one is a string, foo bar, foo bar, foo bar, these are strings. And you see 0 or 1, TRUE, the text TRUE is in the lexical space of the Boolean type. In other words, you can read it as a Boolean, the Boolean true, right? Who is with me? Right, very good. What else do we have? Well, I can also say the element must be empty, then you just write a complex type sequence and you just don't put anything inside. It's the same thing as here, but you don't put any element declarations inside. Who agrees that the above is valid against the type? Yeah, very good. Oh, by the way, I was a bit lazy because you might have seen it's so verbose. Normally, there's always excess schema and so on. I just only showed the relevant part in there. Right, you notice there is, of course, all the excess schema and so on, but I just didn't want to overload the slides. A schema always has the excess schema at the top, and there is the element, person, and so on, in that case, element foo. Okay, but I just wanted to focus on specifically the definition of basically that part right here, the complex type part right here, and right here with an empty sequence. Okay, so that's empty content. And finally, you might remember that XML is very popular with the publishing industry. And so in XML, we love it when we have text intermixed with elements, like to make it apply styles or paragraphs or bold, like thick of HTML, right? So the publishing industry. So it means that we would like a way to mix them. So how can I build a schema that basically allows some text and then an element and then again some text? It's very easy. You just put mixed equals true and that's it. The moment you put mixed equals true, it means you can put text in between the elements. So if you look at this, we have a sequence that only allows B. In that case, I only allow to make it bold. Basically, it's a bold, could be interpreted as a bold marker. That's the HTML tag. And I'm saying any number of times I want, you can put anything as bold as many times as you want, 0 unbounded, right? And it must be a string inside. So here I have a bold, so it doesn't nest. I cannot have further elements. So this is just text in there. And the mixed equals true allows me to have here this some text and some, that is basically a direct text child of foo. And it allows me to have this extra text here that is also a direct text child of foo. So this is not an element. This is not an element, right? This is text. This here is an element. This is the only child element. So in the information set, foo has three children, this text node, this element node, and this text node. Who agrees? Right. And so the magic thing is mixed equals true. That allows you to intermix text in between the elements. Yes?
What happens if text and italic text, then some bold text again? We really have to redefine the element B again?
You mean to nest within B?
Inside of foo, we have bold, then some italic, then some bold again.
Oh, you can absolutely have that because you see I say unbounded here. The unbounded means I can have 1,000 element foo, element B here. I can have it 1,000 times in there, and that's totally fine.
It doesn't need to be.
Well, technically, you can put text in between as much as you want. That's what the mixed means. You can have text B, text B, text B, text B, all you want. Oh, yes, I. So here, no, because it's not in there. If you also want to allow I, then you would need to add the I in there. However, you might have guessed that then the sequence is not appropriate because that would force you, basically imagine you're writing a book and your publisher tells you you first have all the bold text and then you can make it italic, but you cannot alternate bold and italic, right? So of course, it just means we wouldn't use sequence. It's advanced, there are other things than sequence. There is one that basically gives you a choice. It's called excess choice. And then you can put excess choice with B and I, and then you can just have B and I, right? That's already advanced here, but you can do it. You can absolutely say you want just these elements and in any order and any number of time. You can have it. Did I answer your question? Yeah. All right. Very good. Any other questions? Don't hesitate to ask questions. Makes me happy when you ask questions. Yes, I see a raised hand over there. Numbers instead of the text. So at which points?
Like some text, some text. Instead, I wanted to have integers.
I think that in order to restrain it, to restrict it to being numbers in between B, you would need to be a super advanced user that uses a super advanced feature that allows you to write a script to say what constraint it must fulfill. So I don't think there's an easy way to just do it off the shelf. You would have to use some advanced feature. It's allowed, right? XML schema has that. Also, JSON has it. I didn't show you. So you might have in a schema language a way to just write code that says whether you accept it or not, right? It's called the user-defined constraint or something. And then, of course, you know that when you write code, it's Turing complete, right? So the moment I tell you you can write whatever code you want, you know you can do anything that can be computed, right? Okay, awesome. Any other questions? Yes, over there. Go ahead.
Could you also specify that it needs to start with bolded text and can then have like normal text and like bold and whatever?
You mean what's inside the B element?
Like inside foo, that like the first word needs to be bolded and then it can be any type of text or bold.
Oh, yes. So basically, that's the idea that when you put mixed equals true, that does not constrain the text in any way, right? So it can be any sequence of characters. And if you want to restrict that, you would have to write code for doing that. Was it your question or, yeah? Awesome. So mixed equals true just means you can put whatever characters you want, whatever text you want in between the tags, but it doesn't validate any type or anything. It's just text, right? Any other questions? None? And on Zoom also not? Okay, then let's continue. So again, that's a special publishing industry, right? It's the publishing industry that does that sort of things. What about attributes? Well, it's the same idea, right? You can specify an attribute here for that element person. So here you have the child elements. And then you say I have an attribute, birth, that must be a date. And you see this here, 1879-03-14, who is born on that day? Does anybody know who is born? Oh, yeah, it's written here, sorry. Yeah, it's Pi Day, that's how I remember it. It's 14th of March. So yes, this here is text that belongs to the lexical value space of the type date, and so it validates successfully as a date. So it's the same types again, right? Doesn't matter if it's an element or if it's an attribute. The atomic type list is exactly the same one, right? And once you put it in memory, then you replace it with some date object that is much better than just text in the memory. Okay, who is still with me? Right, okay, so we have the attributes. And finally, and I'm done, I won't push anything else, but you should still read the textbook and use Oxygen to train a bit your validation skills. I'm just giving an example of the same great language game that I had in JSON. That's how you would probably put it in XML. Of course, there's more than one way. I decided to just put the sample as an attribute here because it's kind of an ID, and the rest as nested structures. You see again this nested structure with a plural form and then repeated element in the singular form. That's very, very common in XML. And there's the schema on the right, you see. Guess is a string, target is a string. Sorry, I cannot read. Country is a string. Now we have choices, which is a complex type with an unbounded number of choice elements that are all strings, which is the case here. Then I have dates, which is a date. You see that's in the lexical space of a date here. And sample is a hex binary. That means it's a binary, it's a sequence of bytes expressed in hexadecimal. So this here is again text, well, more exactly an attribute value that is in the lexical value space of hex binary because it's all characters between A and F and digits between 0 and 9. So you can parse it as binary, right, in base 16. Who agrees this document is valid against that schema? Right, very good. You can try it in Oxygen actually to validate it. I think I probably did that to make sure that it's correct. So Oxygen is really allowing you to do that. And for the ones of us who love advanced math and so I'm a geek, so I obviously love that. There is a schema of schemas, because you probably noticed if the schema is an XML well-formed document, then maybe it's also the schema itself is valid against another schema, right? So it turns out that we do have a schema that specifies the schema against which the schemas must be valid. And what is awesome about this one is that it's valid against itself, right? That's amazing. It's really valid against itself, like the instance and the schema at the same time. And that's just beautiful. There's the same thing for a JSON schema. You have a schema of schemas. For JSON, you have a schema of schemas. So it's very, very meta, right? It almost becomes theoretical computer science at this point. You can look it up, by the way, if you want to find it. It's on the internet, the schema of schemas. You just need to know that it exists. That is XML schema. Again, I'm taking a step back. What did we see? It's exactly the same logic as for JSON validation. We just want to enforce constraints. We want to say there's these specific elements with these specific types, with these specific attributes, with these specific types. It's all about constraining the structure of an instance. We saw that XML schema is in the XML syntax, JSON schema is in JSON syntax, and so on. So try to take the distance and really see this from an abstract perspective. Right? Any questions? Yeah.
I was wondering about the hierarchy because, for example, looking at HTML, you have stuff like divs, and divs can be like arbitrarily deep in their hierarchy. Mm-hmm. Is there a way? I think we haven't seen it for JSON. We haven't seen it for XML.
Yeah, it's only because I didn't want to scare you too much.
Okay.
But it's absolutely correct that basically the way it works in XML schema is that you can basically define elements with this tag at the top level behind schema and give them you give them a name. And then what happens is that you can refer to them. So you can define an element with a specific type, and then at plenty of other places, you can refer to it. So you can basically define, for example, in HTML, an element B and div and span and so on, that can be at all levels, and then you refer to them. Like in a div, you can say, I'm referring to span that is allowed in there, and so on and so on.
So it's self-referring then.
Exactly, you can refer to already defined elements, right? Then in order to do that, it's just that when you nest in there, let me take an example. Yes, here, you basically say name. So here you define the element. Instead of name, just use ref. And if you use ref, then instead, then you wouldn't put the type because that's you're referring to an existing one. That would refer to another element somewhere else in the schema, right? You just use the ref attribute instead of the name attributes. It's already an advanced feature.
Thank you.
Okay. Yeah. Oh, yes. Give that back to you. Yeah. Goodbye. Thank you. All right. So if everything is good, well, of course, you need to train, you need to use Oxygen, you need to write schemas, you need to write the textbook, but you have the high-level knowledge now. So the next step is that I would like to connect this to data frames. And so the idea actually probably is intuitive to you. Who agrees that if I have this JSON schema in there, ID integer, name string, leave-in Boolean, and I have data in that format, let's say I have 4 JSON objects, do you agree it fits in a table like this? Who agrees? Right? Very good. So you see, it's just columns because it's flat. There's no nested objects in there. ID, name, leaving, ID, name, leaving. And here I have 4 records. Every one of these would be a JSON object. Who sees the 4 JSON objects in there? Who could reconstruct the 4 JSON objects? Right? Very good, majority. So otherwise, do it as an exercise, right? But basically on the right, you have 4 JSON objects, but instead of showing them syntactically, I show them as a table because it's more intuitive and it's logical, right? Because we know it's valid against the schema. So there's this idea that when we validate against the schema, we can kind of have more visually appealing representations of the data, thanks to the schema. In fact, that schema is very close to a create table statement in PostgreSQL, right? Create table people, then ID integer, name text in PostgreSQL, leaving Boolean, and so on, right? So that's very close to a table schema. Then we can also have empty values, because you remember that in JSON it's all optional. So you could have also missing keys. So let's say I put an exclamation mark in ID because this one must be there. You see the exclamation mark, but name and leaving are optional. And so here I just don't put anything. Who agrees we are breaking relational integrity? Okay, and that's fine. That's a totally common thing to do. Even in PostgreSQL, you can have null values, right? So that's totally fine. And you put not null if you want to insist that it's there. So we are breaking relational integrity. But wait, there's more. Because it's JSON, so we can have nested structures. And you remember that we could have here an array of strings. So if I have an array of strings, technically I could represent it in that way, right? I have two strings in here, one string, two strings, one string. This is an array. You notice it's no longer a table, right? The way I drew it, it has these lines that don't go all the way, right? But nevertheless, could you reconstruct the 4 JSON objects? Who would be able to do that? Okay, do it as an exercise. Otherwise, try to reconstruct the 4 JSON objects. They must be valid against that schema, the 4 JSON objects. Okay. Now I could also have nested. So here it was a nested array. Here it's a nested object. So then I can just draw it like this with subheaders, first and last. And then it looks again a bit like a table, but technically it doesn't have atomic integrity because it's a nested object. So you could flatten it by having name.first and name.last, and then force it to fit with a hammer into a table. But you agree it doesn't have atomic integrity because there's a nested object, right? Who agrees? Right, very good. Okay, so that's with nested objects. And now we can have nested tables, right? So it's arrays of objects. We have a list of objects with name type. Do you see the array of objects here? Right, it's an array, that's the first object, and that's the second object. Do you see it's a nested table here? These arrays of objects, who sees the nested table? Right, very good. Okay, so that's very common. These are all called data frames, in fact. These are data frames that's represented like this. There's also something a bit different that is common to do. I'm not sure for what reason, sometimes efficiency. It's done, for example, by high energy physicists for the way they store their data. Instead of an array of objects, they invert it and have an object containing arrays. It gives you more flexibility because when you do that, the length of the arrays don't have to be the same, right? This is an array, this is another array, so there's no reason they would have the same length, right? So here there's 2, here there's 3, here are 2 elements, 1 element, 3 elements, 2 elements, and so on, right? Who would be able to reconstruct the JSON objects from that data frame, right? Very good. Again, do it as an exercise. They just need to be valid against what is on the left. So basically, if your schema is well behaved, you can basically turn it into a visual data frame like this. What do I mean with well behaved? It's kind of intuitive. The first thing is that you want your object types to be closed, no additional properties. Because if you have additional properties, you will not fit them in a data frame, right? It's totally unpredictable, and every record would have attributes that are not known in advance. So for whom does that make sense? We want closed object types, no extra attributes. Right? Very good. That gives us predictability. We know the columns of the data frame in advance. The second thing for a well-behaved schema is that I only have concrete types. I cannot just say that's an array or that's an object. I need to specify an array of what, and I need to specify an object with what keys and with what types. Right? So we don't allow abstract types like item, like anything, or array, or objects. Right? Who is with me? Right? So I can have string, date, hex binary, everything in the menu, but not abstract data types, only concrete data types. And no union types because I want domain integrity. So I want in every column to have a specific type in a data frame. Who is with me? Right? For whom is that intuitive that if I give you a JSON schema, let's say, that behaves in this way, you can draw a data frame. Right? That's the idea. So now you have the connection between pandas and all these, what you see on social media with all the influencers that tell you how to use pandas. Now you see a data frame is just a collection of JSON objects that are valid against the same schema. That is well behaved like in here. This is what a data frame is, technically. So you see that JSON schema basically gives you a language for a data frame schema as well. But wait, there's more. Because basically, a lot of things happened with semi-structured data in JSON and XML. At some point, there was even a big announcement of $1 billion invested into MongoDB and so on. And of course, when that happens, you know, FOMO, fear of missing out. And everybody just rushes into this. And so many database systems did exactly that. So what did they do? They extended the system with arrays and structs and JSON and XML. So you see PostgreSQL is just one example. Here you see that you can define arrays also in PostgreSQL like here. You can also use them as complex types basically. In other words, you've just extended relational database systems to break atomic integrity. Right. This is what we are doing here. We already kind of can break relational integrity because of the nulls. So that's kind of always been tolerated. But now we are breaking atomic integrity in a relational database management systems, which makes my cat, feel like this already a little bit. And then you can also put JSON and XML and so on. That is also PostgreSQL, right? So you can put XML, you can put JSON and so on. And of course, the cat is also not very happy about this. And it's even worse than this, because at some point, some people starting having the great idea to create a column type called variant that is just anything. You can put absolutely anything you want in the column. And then two things happen. First, it gets very slow because that's very inefficient. You cannot store it as efficiently as a good old data frame with domain integrity, atomic integrity, and so on. And second, it's terribly difficult to write queries. Like, for example, this is the sort of things you end up writing, right? So basically what you notice is that the moment you start doing that in existing systems, you're pushing them outside of what they were designed for. It's like putting this square peg into the round hole, right? This is not what a relational database system is for, but good news, there are systems that do that very natively and efficiently. MongoDB is just an example we'll see in a few weeks. There's many others. These are known as document stores. And as I will show you later, the SQL language becomes also inappropriate for this. You can actually extend SQL to deal with this, but from a productivity perspective, this is really not easy to write queries that are going to process that kind of data, which is why there is JSONic and 30 other languages by now that allow you to process that kind of data more easily as a user. All right. Any questions so far? All right. So what you've learned, because I'm going to stop here because I see it's already 58. I just have a few more slides. I'll finish tomorrow. Basically, we can constrain the data with schemas and a collection of valid JSON documents, if the schema is well behaved, is a data frame. And we saw that we can push relational systems to their limits, beyond their limits, but then you might want to pick other technologies if you want to break atomic integrity. So I think that's it for today. I hope you enjoyed it. Thank you very much, and see you tomorrow at 9 a.m.